So let's continue practicing putting together proofs in set theory. Here we have a theorem. If A is a subset of B, then A union C is a subset of B union C. So we begin our proof by letting X be an element of A union C. So our assertion is this universally quantified for any X. If X is an element of A union C, then X is an element of B union C. Since it's a universally quantified statement, we just let X be arbitrary, but the hypothesis is that X is in A union C. So we have this universally quantified conditional statement, so we assume its hypothesis. Then X is either in A or X is in C, and that's just the definition of a union of two sets. Since we assumed X was in A union C, we know either one of these is true, not necessarily both, and we don't know which one. Which lends itself to a proof by cases. One of the things we can now work with is this disjunction. We know what conclusion we're after. We're trying to show X is an element of B union C. However, we do not know which of these two is true, but we do know one of them is. So possibly X is in A. If we can show that X being an element of A leads to X being an element of B union C, and we can also show X being an element of C leads to X being an element of B union C, then our proof by cases will be complete. If this, then in here. If this, then in here. Also, we have one of those two things. Therefore, proof by cases, X is an element of B union C, and we'll be done. So we begin our proof of the first case. Maybe X is in A. Typically, proof by cases comes up a lot in set theory because anytime you have an element of a union, you get yourself a disjunction or an or statement, and you don't know which is true, so you proceed by a proof by cases, possibly the first or maybe the second. So if X is an element of A, then X must be an element of B. Why is this? It's just universal modus ponens, okay? X is an element of A, and we were given that every element of A is also an element of B. So since we have X is an element of A, then X must be an element of B. And therefore, X is an element of B union C. This is just introducing an or sign. If X is an element of B, then we can conclude either X is an element of B or X is an element of C. In other words, it's in the union. That's just generalization. Okay, case 2. Okay, we've now completed if we assume X is an element of A, then we derived X is an element of B union C, but we don't actually know that X is an element of A. It was also possible that X is an element of C, so that begins case 2. Well, if X is an element of C, we can directly end up at stating X is an element of B union C. Again, that's just generalization. So if X is an element of A, then we can end up in the set B union C, but if X is an element of C, then we can also end up in the set B union C, and we know either X is in A or X is in C. So the way we phrase that is we say, in both cases, X is an element of B union C, which concludes a proof by cases. If this, then that. If this, then that. One of those two hypotheses must be true. Therefore, the conclusion must be true. So by assuming X was an element of A union C, we derived X must be an element of B union C, using the given, of course, that A is a subset of B. That came in right here. Here's how you would typically see it written in a book. Let X be an element of A union C. If X is in A, then X is in B and therefore in the union of B and C. But if X is in C, then similarly X is in B union C. The sort of formal invocation of a proof by cases by this phrasing in both cases is not always given. It's not always written as case 1, case 2, but I do really recommend when you're first starting to put together your proofs, try to write this much. It's more writing, but it more clearly follows the format of a two-column proof, okay? Assumption, this is a definition, okay? Assumption, conclusion by modus ponens. And then a conclusion by generalization. Assumption, conclusion, conclusion. I mean, it follows the format more closely. It will help you bridge the gap. Okay, moving on. Here's another example. If A minus B is equal to A, then A and B are disjoint. Now, in order to prove this, we need to remember definitions. What is the set difference? What does set equality mean? And what does the word disjoint mean? All of these definitions are important, and you really have to commit them to memory. A proof, assume to the contrary that A and B are not disjoint. Okay, so our assertion was A and B are disjoint, so let's assume to the contrary that they are not. This is doing a proof by contradiction or an indirect proof. We're assuming exactly the opposite of what we asserted, and now we're going to derive a contradiction. If A and B are not disjoint, there must be something that is in A and the same thing, X, is in B. This is just based off the definition of being disjoint. Two sets are disjoint if their intersection is empty. If we assume, therefore, that two sets are not disjoint, their intersection is not empty. What do I know about a set that isn't empty? It contains an element. So there must be something in the intersection of A and B, and I'm going to existentially instantiate that with the variable X. Okay. If two sets are not disjoint, their intersection is not empty. If their intersection is not empty, something exists in it, and you can existentially instantiate that using a new variable that something must be in the intersection of A and B, and therefore it's in A and in B. If X is in B, then X is not in B complement. That's the definition of complement, right? The elements that are in the complement are not in B, and vice versa. So if X is not in B complement, then X is not in A intersect B complement. If it's not in this set, it's not in the intersection of these two things. Okay, that's just a disjunction in De Morgan's laws, but it's pretty straightforward. And therefore, there is some X which is in A, specifically this X, but is not in A intersect B complement, which is the same thing as A minus B. So there is something that is in A, but not in this set. And therefore, the sets are not equal. Remember, two sets are not equal if there is something in one set that is not in the other. But that exactly contradicts our given that A minus B is equal to A. And that's the definition of set equality. Two sets being equal means they're subsets of each other. So if two sets are not equal, one of them is not a subset of the other, meaning one of them must contain an element that the other does not. And we have here, there is some X that is an element of A that is not an element of this set. Therefore, those two sets aren't equal, but we were given that they are. And here's how it would generally be written in its like super abbreviated form. Assume to the contrary that there is something in A intersect B. This is sort of quickly telling your reader, oh, they're not disjoint. There is something in their intersection. Then this X isn't in A minus B, contradicting the given. How would you get straight from here to here? Well, that's laid out in these steps, and honestly, a lot of textbooks would sort of skip right over that, leaving out so much detail that students who are just learning how to put together proofs get a little lost. So as I said before, I recommend trying to include more detail rather than less. But if you come across proofs online or in other books, and you can't quite follow all the steps and you're not sure what's being said, by all means, try and search out other sources that have more detail in them. So here's a new example. The power set of A intersect B is equal to the power set of A intersect the power set of B. We're claiming two sets are equal. How do we generally prove two sets are equal? We have to prove that the set on the left is a subset of the set on the right, and then we will show that the set on the right is a subset of the set on the left. So we have two things to prove: left subset right, right subset left. So let's start with the first one. We want to prove that the power set of A intersect B is a subset of the power set of A intersect power set B. That is a conditional statement. If something is in this set, then it is in this one. So we start our proof by assuming, okay, let's suppose X is an element of that set on the left. Our goal now is to show that X must be an element of the power set of A intersect power set of B. What does it mean for X to be an element of a power set? X is a subset of that thing. So since we assumed X is an element of this power set, it must be a subset of A intersect B. We now claim, in other words assert, that X is actually a subset of A. How do I prove X is a subset of A? That's a conditional statement. So assume Y is an element of X. Notice that now X is some sort of set. It's a subset of A. Since X is a subset of A intersect B, if Y is an element of X and X is a subset of that, then Y must be an element of A intersect B. Therefore, Y is an element of A and Y is an element of B. Specifically, Y must be an element of A. So if Y is an element of X, then Y is an element of A. That proves X is a subset of A. So let's look at what we've done so far. We were trying to prove the power set of A intersect B is a subset, at least, of the power set of A intersect power set of B. We began with an arbitrary element of the power set of A intersect B, therefore it's a subset of A intersect B. We claimed that it's actually a subset of A, and we've proven that. In other words, X must be an element of the power set of A. If X is a subset of A, then X is in the power set of A. That's what the power set is, remember, all subsets. Similarly, X is an element of power set of B. All of this argument here can be repeated by replacing all of my capital A's with B's and vice versa. So since X is a subset of A intersect B, we were able to conclude that it must be a subset of A. But intersections are commutative. Left versus right doesn't matter. So if X is a subset of A intersect B means it's a subset of the set on the left, it must also be a subset of the one on the right. So if X is a subset of B, it is an element of the power set of B. Since X is in the power set of A, and X is also in the power set of B, it's in their intersection. Overall, what have we shown? Assuming X was an element of power set A intersect B, we've shown X must be an element of power set A intersect power set B. AKA, the set on the left is a subset of the thing on the right. We're exactly halfway done proving this theorem. We have shown that the set on the left is a subset of the set on the right, and now we just need to go the other way. Well, how do I show that this is a subset of this? Assume we have an element of the set on the right. Well, if it's in the intersection of two things, it's in each one individually. If X is in one power set and X is in another, then it's a subset of A and also a subset of B. What do we now need to show? We need to show X is an element of the power set of A intersect B, which will follow if we can only show it's a subset of A intersect B. However, we do know X is a subset of A and X is a subset of B. Okay, so we've made an assertion, a claim. X is a subset of A intersect B. So how do I prove that? Assume you have an element of this set on the left. We just need to show that this element Y is also an element of A intersect B. But X is a subset of A, and Y is an element of X, so Y is an element of A. X is a subset of B, and Y is an element of X, so Y is an element of B. So since Y is an element of A and also an element of B, it's an element of their intersection. So starting from an arbitrary element of X, that must also be an element of A intersect B. In other words, X is a subset of A intersect B, and therefore is an element of the power set. So having assumed X was an element of this intersection, we were able to conclude that X was an element of this set here. In other words, the set on the right, this intersection of two power sets, must be a subset of the thing on the left. So we've shown left subset right, and then we showed right subset left. That's a proof by mutual containment. The two sets must be equal. Okay, so this proof is longer than ones we've done before, but every line follows quite quickly from the one before it. The claim, two sets are equal. How do we prove that? Left subset right, which is here, and right subset left, which is on this side. Each one of those follows a pretty predictable format. How do I show something as a subset of something else? Pick an arbitrary element of the set on the left and show that it must be an element of the set on the right. Or pick an element of the set on the right and show that it must be an element of the set on the left. And then you fill in the steps accordingly. Okay, so the format hasn't really changed, it's just more steps. Okay, moving on, it's worth discussing what are called counterexamples. If a universally quantified statement is false, then its negation is an existentially quantified statement, which is true. Remember, once you negate a universal quantifier, you can pass the negation through the quantifier symbol and it changes which one it is. So a false universally quantified statement becomes a true existentially quantified one. So the rules of existential generalization, in other words, I want to show an existential statement. If I want to do a universal generalization, I just need to have one specific example. Okay, so if you want to make a universally quantified statement false, what you want to do is make an existentially quantified statement true. How do you get existentially quantified statements? Through existential generalization, but that's a very liberal and freewheeling method, meaning all you have to do is find one time that it's true, then you can existentially generalize it. If it was true once, then there exists a time when it's true. In other words, okay, to show a statement is not always true, you just have to find a single time that it's false. Such things are called counterexamples. So, show that the following claim is false. A intersect B union C is equal to A intersect B union C. This is not true. If this is not always true for any sets A, B, and C, then it must be possible to find sets A, B, and C that make it false. Okay, so since this is implicitly universally quantified, this is saying for any sets A, B, and C. To find a counterexample, we don't need to show that this always fails. We just need to show it fails once. So we can be extremely specific and explicit about what sets A, B, and C are going to make this claim fail. Let's let A be the empty set, B be the empty set, and C just have a single element. This isn't the only way we could do this, but this is one. So what's A intersect B? Union C. Empty set intersect empty set union this. What's empty set intersect empty set? Empty set. Okay, what is in both the empty set and the empty set? Nothing. Then I union this with C. So I ask, let's take all the things that are in the empty set, but also all the things that are in this set, and I just get that set back. However, what if I tried to do the other side? A intersect B union C. Empty set intersect empty set union this. So in this parentheses, we have the empty set union this set, which is just that same set. Okay, if I union the empty set with something, it doesn't really add any elements to it. Now I have empty set intersect this. What is in this set that is also in the empty set? Nothing. So on the one side, we got the set containing C. On the other, we got the empty set, and these are not the same set. So since those are not the same set, these two things are not always equal. So by constructing one particular example where this was false, we have actually shown that it is not always true. So a universal statement might be false even if it is sometimes true. So for example, if A, B, and C were all the empty set, this would actually work out. You'd get empty set equals empty set. We're not saying this is always false. We're just saying that it is not always true, meaning it is sometimes false. So how do we get practice generating counterexamples to false statements? It's a very, very useful skill, in my opinion, to develop. Generating counterexamples to false statements is great practice using definitions and getting used to manipulating them. To effectively generate counterexamples, you have to be incredibly familiar with those definitions and know how to work with them, and that's why it is a good skill to develop. Also, frequently in math, especially once you get to, say, the research stage, you have statements and you don't really know if they're true or not. Trying to show a statement is true or trying to show a statement is false are two different skills, and they're both necessary. So counterexamples only need to exist in one particular way. But if the universal statement is true, you have to prove it using very general techniques. So typically, if you don't know whether a statement is true or false, if it's false, it will be easier to show that than if it's true, it will be harder to show that it is true. So spend some time trying to show it's false first, because if it's false, that'll be faster. So a point of advice, start with simple constructions before trying complicated ones. In my experience generating counterexamples, students rush to large sets with a great many elements, which it might still work compared to simpler sets with fewer elements, but it's more time writing and more confusing. Try to work with the simplest sets that you can to generate counterexamples. It makes the presentation much more efficient. Okay? So try using empty sets or sets with one or maybe two elements. Okay? It's actually quite rare for a counterexample in an introductory course like this to require any sets to have more than two elements. Okay? Most counterexamples that you're asked to generate can actually be done just with sets with one, sometimes two elements. In a complicated counterexample, it's not less correct. If you use sets with 45 elements to generate a counterexample, and someone else uses sets with 2 elements, you weren't less correct. It's just possibly more confusing and can make someone reading your work, it can make it harder for them to follow what you're saying. So smaller sets lead to cleaner counterexamples, assuming that it still works.